Hello everyone, I'm Cameron Hicks, and this is my video report for Physics 2211. In this video, we are going over Lab 1, Constant Velocity, Rolling Motion, Theory versus Reality. In this lab, we tracked an object moving in a straight line at constant speed. The goal is to analyze its motion using Tracker, a video analysis tool, and then create a computational model that predicts that motion. This is a great example of how physics isn't just formulas on a page. We can actually predict real-life motion using those formulas on a page and math. By comparing observed data to the model, we can see how well Newton's second law describes motion in practice. And these are just some of the main physics principles and models. We have Newton's second law, net force equals mass times acceleration. The momentum principle, the net force of an object equals the rate of change of its momentum. Because the object moves at constant speed, the net force is effectively zero. And we have to assume that friction and air resistance are negligible, because in the computational model, we can't accurately incorporate a way that calculates friction and air resistance. And within the parameters of our experiment, which we will go over, we can see that friction and air resistance are not needed to accurately gauge data. And these are some of the system and initial conditions. And the observed system is the small metal cylinder. It was about an inch or two in length, and the surroundings were a flat table surface, an unobstructed path, and stationary camera. The initial conditions were position at t equals 0 meters, at m equals 0, x equals 0 meters, excuse me, at time t equals 0. And the velocity was about 0.66 meters per second. And this was derived from the tracker, which we then incorporated into the glow script code in the computational model. And for our calibration, we used a meter stick on the table surface, and it's in camera view of the actual motion of the object. And since we have such a small distance, air resistance and friction were not exactly needed to accurately gauge the data. And this is the observational data. Using Tracker, we recorded the object's position at discrete time intervals. Each point corresponds to the object's location at a specific moment. Then we exported this data to a spreadsheet to plot position versus time. You can see that data points form a nearly straight line, which indicates the object is moving at almost constant velocity, which then in turn indicates that the net force is 0. And this is just the video demonstration of the tracker and the actual physical video. And now we're on to the computational model. To model the model computationally, I use GlowScript sorry code. The model takes the initial position and velocity from tracker and assumes 0 net force. The program then calculates the position at each time step, generating predicted position versus time data. Because the net force is 0, the velocity doesn't change, and the predicted positions form a straight line. And then this is the screenshot of the code. In order to summarize this, I just implemented the velocity that we got from the tracker. And then since the amount of time it took to go from 0 meters to 1 meter was 1.54 seconds, we put that in the while loop. And then effectively, we can calculate the or predict the motion by using this little code sequence. And then this is the results. The results are this data on the right, and then this graph right here. And then now we are on to the comparison of the observation versus model, where we compare the computational model to the tracker data. And now we can see near perfect agreement. The model produces a straight line, and the observed points fall almost exactly on top of it. Minor differences may appear, and this is mainly due to the errors that we will discuss in the coming slides. But effectively, we can conclude that we can use physics to predict real-life motion. And these are just some of the possible errors for why the alignment of the tracker and the actual glow script code was not perfectly identical. And these errors include camera angle may not be perfectly perpendicular to the motion. Tracker calibration may have minor inaccuracies since we have to manually input the marker steps for the cylinder and when it's moving. And then there may be some slight inconsistencies in the table surface, though it was more or less pretty flat. And then there's obviously some friction, but within the parameters of our experiment, it's not really necessary to incorporate. And then just some discussion and additional questions. We can obviously conclude that constant velocity is the cause, or I guess the justification for why net force equals zero. And then when multiple forces act, but vector sum equals zero, this can be concluded up to Newton's second law. And then some just basic additional questions. What if the axes were flipped? Then the graph would now have a negative slope. Because as you could see in the other graphs, it had a positive slope. It was direct correlation. But then now, if the axis was stopped, it would go like that. It would be negative. And then motion physics unchanged. And then just to reiterate the possible errors, the video parallax, timing inaccuracies, and calibration misalignment. And to conclude, the tracker data did match the model closely. The best fit velocity was 0.66 meters per second, and it does support Newton's second law, which is net force equals zero, which then iterates that momentum is constant and that there is steady velocity. So thank you for watching, and I hope you enjoyed.